So what we're getting into today and for the next couple of weeks, or next couple of sessions here, we'll be here for about 2 weeks, is reactions in aqueous solution. Now, the reason we focus so much on reactions in aqueous solution is mainly because these reactions are kind of the majority of the reactions that we see in the laboratory. So think about the experiment that we just did, the copper cycle lab. Every single one of those experiments, every single one of those reactions either involved something that was in solution or was making a solution and having the reaction take place in the solution. So you start with the copper metal, you add the nitric acid to it. That nitric acid is a solution, and it dissolved and reacted with the copper and put it into solution. And then every step that you did along the way involved some sort of aqueous component, some sort of water-based product, either being generated or being used as a delivery method. So these kinds of things are important, and they're stuff that we see a lot of as we progress here. Now, as far as sections go, there are 6 primary sections in this module. We're going to spend the majority of our time in this unit talking about the first 4. So we're going to talk about solubility today. Friday and Monday, we will talk about precipitation and acid-base neutralization reactions. Next week, we'll talk for 1 day about electron transfer, and then we'll spend a couple of days talking about how to use all that stuff that we just did with stoichiometry and apply it to solutions, because while there is a lot of common ground, there is a little bit that is different as well. So let's start by kind of fundamentally defining our terms. What does it mean to be a solution? What is a solution? What goes into a solution? So solutions are homogeneous mixtures. So if you remember back to module 1, maybe the second lecture that we had, we talked about homogeneous mixtures, the idea that there are physical combinations of substances that have a uniformity of appearance. Solutions have 2 primary components. We have the solvent. The solvent is the thing that is doing all of the dissolving. It's the stuff that's present in the greatest amount. And for most of our solutions, we're talking about water here. So the thing that dissolves all of the other things. Solutes, on the other hand, are the things that are actually dissolved. So these are the substances that do get dissolved in the process. So for aqueous solutions, these could be things like ionic compounds. They could be things like alcohols. They could be things like sugar, salt. Anything that dissolves in water could be considered a solute. And so this last line here is really important to us, because what this last line tells us is that when we make a solution, it's okay to have multiple solutes. Look at any commercial drinking product. You're going to find that in that solution of Powerade, in addition to water, you're going to find 34 other ingredients, including different kinds of salts, different kinds of dyes and colorants, different kinds of flavoring agents, along with anything else that they want to add in there, whether it be vitamins, minerals, you name it. In the end, the water is the solvent in that particular sample. Water is the thing that is present in the greatest amount. Everything is dissolved in the water. But the other 34 ingredients, those are all solutes. So it's perfectly okay to have multiple solutes, but you can only have one solvent. Because there can only be one thing that is present in the greatest amount. When we talk about solubility, which is the primary topic of today, there are a couple of things that we want to think about, a couple of things that we want to consider. First of all, our primary focus is on aqueous solutions. Aqueous solutions are solutions, homogeneous mixtures, where water is the solvent. And when we talk about solubility, we're talking about a couple of things here. First of all, we're talking about the ability of a substance to dissolve in the water. Now, the means by which this happens is something called hydration. And so what we need to think about in solution formation is that there's basically a three-step process that's going on here. The first thing that has to happen is that the solvent has to separate itself from itself. So when we think about liquids, we know that those liquids are all kind of on top of each other. Every molecule is touching several other molecules. So the first thing that happens is that we have to create room for the solute. So the solvent starts to break apart, starts to add space in between itself. Now, the reason why it does this is that the solvent is going to interact with the solute. So our solute usually is going to be resembled in some kind of way as either a crystalline structure if it's a solid, or if it's another liquid. All the liquid molecules, again, are all mangled on top of each other in this very condensed kind of way. So solvent has to sort of dissociate from itself. It starts interacting with the solute. And then the third step is hydration. And in that third step, what we see is something like this, where the molecules of water start to surround the molecules of the solute. So if it's an ionic compound like this, we'll see that it's going to front itself according to charge. So we haven't talked about this idea specifically about polarity or about charges in terms of intermolecular forces. But what we do know about water is we do know that it is polar. And so being polar, that means that there is a positive side of water, that side around the hydrogens, and there's a negative side of water, that side around the oxygens. When water dissolves other things, it's going to dissolve other polar objects, other things that have positive sides and negative sides. So in the case of an ionic compound, those positives and negatives come in the form of the ions themselves. So the sodium ion, which has a positive charge, is going to attract the negative side of the water molecules, and that negative side of the water molecules will surround that sodium ion and hydrate it. And on the chloride side, we've got negative charge there, so the positive side of the water molecules flip themselves around, surround that chloride ion, and hydrate it. And so a solution ends up being a series of these hydrated molecules moving around in that liquid medium, which is why we have consistency in a solution. No part of a solution is more concentrated than another once we get to this full mixing state. So the key feature, and we'll talk about this more in module 9 when we talk about intermolecular forces, but the idea of solubility falls upon a general principle of what is called like dissolves like. Substances with similar polarities dissolve in each other. So polar molecules dissolve in other polar molecules. Nonpolar molecules dissolve in nonpolar molecules. Since water is polar, the majority of things that are going to dissolve in water are going to be things that are either polar themselves or charged in some kind of way. And so we look at ionic compounds, those have charges. We look at polar compounds, those things that, like water, have a positive side and a negative side. And those are the things that are going to dissolve in water. They're going to have what we call high solubility, meaning more of those compounds can dissolve in water compared to others. Now, because of our solubility here, because of the idea of polarity, there's another term that we need to introduce here, and that term is an electrolyte. So an electrolyte solution is a solution that is capable of conducting electricity. Now, when it comes to electrolyte solutions, they fall into 3 different categories as well: the strong electrolytes, the weak electrolytes, and the non-electrolytes. We're going to talk about each one of those in turn. The things that make strong, the classification of these electrolytes is related to how well they conduct electricity. Strong electrolytes conduct electricity very well. Weak electrolytes conduct electricity, but not terribly great. Non-electrolytes basically don't conduct electricity at all. When it comes to strong electrolytes, what we are seeing in this case is a large quantity of ions. So the characteristic of electronic conductivity has everything to do with ions. Ions stabilize the movement of the electrical current. And so the more ions we have, the more current is stabilized, the more current is going to be able to pass through. So in strong electrolytes, what we're going to see is that there is a heavy character of ions present in these solutions. And so where do those ions come from? Well, they come from the dissolving of ionic compounds. So anytime an ionic compound dissolves in water, it breaks apart into the ions that make it up. Just like we saw with the sodium chloride. The sodium ion gets broken apart and surrounded with water molecules. The chloride ion gets broken apart and separated and surrounded with water molecules. Any ionic compound that dissolves in water is going to create a strong electrolyte solution. In addition to those, anything that is a strong base or a strong acid will also break apart and form ions in solutions. And so it is the ionic compounds, the strong acids, and the strong bases that make up what we would call strong electrolyte solutions. So that's strong electrolytes. Let's talk about weak electrolytes. With weak electrolytes, we are seeing conductivity in these compounds, but what we are not seeing is nearly the same quantity of ions. And the reason we are not seeing the same quantity of ions is because these acids and bases that make up weak electrolytes don't actually break apart that much when they dissolve in water. They definitely still dissolve in water, but when they dissolve in water, they act more like molecular compounds than ionic compounds. So what I mean by that is we have two kind of classic examples here. We've got acetic acid and we've got ammonia. Acetic acid, when it dissolves in water, will break apart into the acetate ion and the hydrogen ion. However, this breaking apart that we're talking about here happens somewhere around less than 5% of the time. So in the chemical world, we call this dissociation. And this is a low dissociating acid. Doesn't dissociate much. Dissociates enough, gives us enough ions that we will conduct electricity, but to a much lesser extent. Most of this stays over here. So only 5% breaks apart. That means 95% stayed together. So for the most part, we're seeing molecules that are staying molecules rather than breaking apart into ions. For ammonia, similar kind of scenario. For the most part, it stays dissolved as a molecule. Only about 5% or less actually break apart into the ions. The remaining 95% stays as a molecule. And since molecules do not conduct electricity on their own, they need charges to do it. These, for the most part, do not conduct electricity very well. Again, there are ions present, so it does conduct, but not to the same level that we saw with the strong electrolytes. The third category is the non-electrolytes themselves. The non-electrolytes don't have any conductivity effect whatsoever. And the reason they don't is because they don't form ions in any kind of capacity either. What we see in these kinds of compounds usually are organic compounds that do not contain nitrogen. So primarily we're talking about carbon, hydrogen, and oxygen kinds of compounds. If there's a nitrogen there, that nitrogen actually can act basically, and we'll get into why in a second. But for the most part, we're talking about things like alcohols. So ethanol, ethylene glycol, both of those are alcohol and alcohol derivatives. Glucose and sucrose, sugars. Organic compounds in general here. They are polar, so they dissolve, but there's no ionic character to them whatsoever. So they don't do anything, at least not from a conductivity standpoint. Let's look at this pictorially so it can kind of give you an idea of what I'm talking about when I say conductivity. So over here on the far right, we've got non-electrolytes. Really cool experiment that you can do with electrolytes is there's a conductivity apparatus that you can acquire where it's basically an open circuit with a light bulb. So the open circuit does not conduct electricity. The two leads are not connected. But if you connect the two leads, electricity flows through it, the light bulb lights up. What you do with it is you put it into different kinds of solutions, and you see if the solution is able to light the light bulb, and that's what is being shown here. So for non-electrolytes, what do we see? Well, we don't see anything. The light bulb doesn't light up because there are no ions in that solution. If I put it into a strong electrolyte, we see that the light bulb burns very intensely, very, very brightly. Why is that? Well, ionic compounds and these strong acids and bases, they have lots of ions in solution. More ions that you have, the better you can conduct the electricity. In the middle here are the weak electrolytes. And we can see that the weak electrolytes, they do conduct. That light bulb is not out. It is dim, but it is not out. So it does conduct electricity, but not very well. And you can see that 95:5 kind of ratio here. This bulb is a lot closer to the non-electrolyte brightness than it is to the strong electrolyte brightness. Why? Well, 5% ionization is a lot closer to 0% ionization than it is to 100% ionization. More ions, more conductivity, brighter bulb. All right, any questions about electrolytes before we take a little side trip here? All right, the side trip that we're going to take here is we want to take a closer look at acids and bases. Now, thus far, all we've done as far as acids and bases has been from a nomenclature standpoint. I can recognize an acid because its formula starts with hydrogen. I can recognize a base because its formula ends with OH, hydroxide. That general rule of thumb is what we have used thus far for identifying acids and bases and trying to name them. The problem with this approach is that it's kind of limited. There are things that are acidic that don't really have that H in the front kind of chemical formula. There are things that are basic that don't have that OH on the backside kind of chemical formula. And so while this Arrhenius definition does allow us to identify the common acids and bases, it doesn't really do much to help us identify the ones that aren't as common, but are still just as acidic or basic. So we need a better theory. We need a better model. One of those better models is something called the Bronsted-Lowry theory. Bronsted-Lowry theory seeks to identify acids and bases based upon their reaction. And so what we're looking for in particular is not so much reaction necessarily, but the movement of protons. Protons being H+ ions. Now, why do we call H+ ions protons? Well, let's think about that for a second. If I have a hydrogen atom, atomic number for hydrogen is 1. So I've got 1 proton and 1 electron. Most hydrogen atoms are just that. They don't have any neutrons. So if I've got 1 proton and 1 electron, and the electron goes away because it's now charged, all that we're left with is the proton. And so H+ ions are commonly referred to as protons for that reason. It's the only way that we can talk about protons moving around, because we know that from a nuclear standpoint, Protons stay in the nucleus and don't move around. But if the nucleus is only a proton, that becomes our exception. So how does the Bronsted-Lowry theory different? Well, again, we're talking about the movement of protons. So we talk about acids, we talk about things that are going to give away protons. So if I look at a chemical reaction, I'm looking for the movement of hydrogen. The thing that loses hydrogen is our acid. The thing that takes that hydrogen is our base. Acids are proton donors, bases are proton acceptors. Now, to add one more wrinkle to this, because of course we have to, it's chemistry. What about substances that do both? Most common example of this is water. Water, because it is H2O, is capable of adding a proton and becoming hydronium ion, H3O+, or losing a proton and becoming the hydroxide ion, OH-. We already know the hydroxide ion. These kinds of substances that can go both ways depending upon their environment carry one of two names. Your book uses the term amphiprotic. You might also hear them called amphoteric. Amphoteric is the same thing, basically. Can act as acid or base. How might that look in a chemical reaction? Well, let's take an example, this one. Hydrochloric acid in water. How do we get an acid out of that? Well, we've identified hydrochloric acid as a strong acid. Why is that the case? Well, look what it does. The proton here the H is moving. It's going from the HCl to the water. As a result, the water has gained that H+, it's now hydronium ion, H3O+. And the hydrogen chloride has lost that proton, it's now just chloride. Since acids are proton donors, we can identify HCl as an acid because it gave away that H+ ion. We can identify the water as a base here because it took that H+ ion. And so under this definition of acid and base, we can expand our footprint. So one thing you should know, the Arrhenius method for identifying acids and bases still works here. Anything that we identified as an acid under the Arrhenius, where's the hydrogen nomenclature kind of name way, still works. All of the hydroxides that we identified as bases under the Arrhenius definition still works. But now we can actually expand it beyond. So let's talk about some commons, common acids, common bases. On the strong side, most of the strong acids that we know and love are the ones that we've been working with most of this semester. Your halide acids, hydrochloric, hydrobromic, hydroiodic. Notice that hydrofluoric HF is not on this list. It's the only halide acid that isn't. Other acids that are strong that we work with commonly, nitric, sulfuric, and then we've got those chloric and perchloric acids there as well. So those 7 strong acids are the only strong acids that we have to concern ourselves with. If an acid is not on that list, and we can identify it either through formula or through action, we know that it's going to be a weak acid, and therefore we create a weak electrolyte solution. Strong bases are a little bit easier to identify. They have a very periodic kind of property. They're all hydroxides. And so the group 1 hydroxides, so anything from lithium down, as well as the heavy group 2 hydroxides, anything from calcium down. Those hydroxides are all strong bases. If it's not one of those two categories, it's a weak base. So again, identifying it by action or by formula. So all of the hydroxides from all of our transition metals, basic, but weakly basic. They're not in one of those two categories. Nitrogen-containing organic compounds, basic by action, not by formula, but by action, but weak. So let's take a look at this question here. Having now discussed all of the different kinds of acid and base theory and everything else, let's go through this one together and let's try to identify what is strong and what is weak. So this first one is acetic acid. If I react it with water, it's going to make H3O plus and CH3COO minus. So based on this formula, we would identify this as an acid. It's donating that H on the very end there. Is it one of the strong acids that we identified on the previous slide? No. So if it's an acid, but it's not strong, that means it's a weak acid. Weak acids are weak electrolytes. So A must be correct. B. We can recognize B as an acid by formula. This is an Arrhenius acid, hydrogen's at the front. Is HCl one of the common strong acids that we identified previously? It is. So as a strong acid, it's not going to be a weak electrolyte, it's going to be a strong electrolyte. That's not going to work. Ammonium chloride, NH4Cl. Is there anything acidic or basic about that compound? No. It's just ionic. I know ammonium ion, I know chloride ion, put them together, I've got an ionic compound. Ionic compounds that dissolve in water are strong electrolytes. So this one's not going to work. This fourth one's kind of a tough one. This one we have to recognize this is an organic with a nitrogen on it. So we've got a hydrocarbon with a nitrogen. This one will react with water to create this reaction. So it does act as a base. It's not even a hydroxide base. So we know that it's not one of the strong ones, which means it has to be a weak base. And if it's a weak base, it's going to be a weak electrolyte. So D's good. HF. We can identify HF as an acid based upon its formula. It's got the hydrogen in the front. So it's an Arrhenius acid. Is HF on our list of strong acids? It's the only halide that isn't. So that means it's a weak acid Weak acids are going to be weak electrolytes. E is correct. All right, F, last one on the list. I got the same makeup as letter A, only I got sodium in the place of hydrogen there. Now, the hydrogen we identified as being acidic. Is sodium acidic? This is an ionic compound. This is sodium acetate. Sodium acetate does dissolve in water. Any ionic compound that dissolves in water is a strong electrolyte. So that will not go either. So 3 of these were weak electrolytes. The other 3 were strong electrolytes. There were no non-electrolytes on this particular slide. Last question, we'll call it a day. How do I identify acid and base? Well, very similar to what we have been doing on the previous couple of slides. I need to follow the hydrogen. I can see that this hydrogen has migrated. It went from here to here because we went from sodium sulfide to hydrogen sulfide. So this compound that gave away the hydrogen is an acid because it is a proton donor. The sulfide ion is the base because it is the proton acceptor. And so even though we don't have a hydroxide here, we still have basic behavior based on that action. So on your way out today, if you did not submit that previous question, make sure that you do so before you leave. Otherwise, hit the stoplight on the way out. On Friday, we will talk about solubility rules. So we've talked about acids and bases. We really haven't talked about the ionic compounds yet. How do we determine if an ionic compound is going to dissolve or not? There are solubility rules to help with that. And that's what we'll talk about Friday. And then we'll talk about how we actually use solubility to predict reactions. Have a good day.